Okay, what we're doing tonight is a continuation of what was covered in the video. Those of you who had 012, of course, had that in 012. In fact, exactly the same material that far. Those of you who did not have 012, hopefully at some point in high school or wherever you had some solving systems of equations at a time. I will be in the process of working where we're going on. I will be doing some of these. You will just get some at the very least in terms of how to do the process. So with that said, let's go ahead and switch to the PowerPoint. By the way, okay, we're going to be using the systems of equations in linear applications. Here is a word problem. Now, in this particular word problem, what I'm going to be trying to teach you right now is not only how to solve multiple equations, but when it's a word problem, how to analyze them and write the equations to work. So that's about as much of what I'm doing as anything right now. In this particular problem, and by the way, this problem and the next problem that I'm going to put up, probably 90% of the years, a problem like one of these two has been on the final. So this is kind of an important one. Okay. Now, in a school play, there were adult tickets sold for $9 a piece. Kid tickets for $5 a piece. There were 400 seats and all were sold. Okay, so the number of adult tickets plus the number of kid tickets have to total 400. All right, well, that's going to be our first equation. It also tells us that if they paid $9 a piece for adults and $5 a piece for kids, that the total sales were $2,600. So let's look at setting this problem up. First, I wrote out my legend. I defined my variables. I chose A and C for my variables because they're kind of representative. Also, when I put in the answer here, I've already got the problems labeled, so I don't lose the label point. Now, my first equation, just like I said up here a moment ago, all of the adult tickets sold plus the kid tickets sold equal 400 tickets. If you look at this, number of tickets, number of tickets, number of tickets for my units. Okay, very uniform there. Now, our second one is going to be the monetary value on these tickets. Well, the adult tickets cost $9 a piece. The kid tickets cost $5 a piece. And the total revenue was $2,600. Dollars. 9 times how many tickets? 5 times how many tickets equals the total money. You remember way back, and I had the picture of my grandson's car and we did the problem with it. And we had to take the percentage of water and the percentage of alcohol to adjust it. This is kind of the same way. And the other problems we did at that time on mixtures and stuff. Okay. Except we're using 2 equations now instead of a single variable, or 2 variables instead of a single variable. Well, to solve this problem, I'm going to do it by what we call the addition or elimination method. Now, in that method, hopefully you watched the video so you know what I'm talking about. I'm going to have to find what I call an opposite pair. I need a pair of values of A's that are opposite. Maybe negative 9A and positive 9A. Or a pair of C's. 5c and negative 5c. Okay, so they'll cancel out, just leaving one variable. Now that's the strategy. So I can do either the A's or the C's. In this case, I chose to eliminate the C's. So I multiplied everything in this first equation by negative 5, resulting in this equation. Well, I just brought this one over. Okay. I have the opposite pair right here. These two go to 0. We add those, we get 4a, here's the 0, and this gives me 600. Well, I divide both sides by 4, and I get the number of adults is 150 adults. Now I've got to find the number of kid tickets. So what I do then is I take this 150 adults and I put it in this first equation. So 150 plus the number of kid tickets equals 400. And therefore there are 200 kid tickets. Now, any questions about anything I did, including the opposite pair idea? All right, anyone not ready for me to switch? Next problem. Okay, this problem is going to be set up almost identically to the last one. This one does have a silly little quirk to it. Anybody in here ever played basketball? How many games have you ever known when a team shot more 3-point shots than they did 2-point shots? Ever? Not that I know of. Well, the answer on this one's going to come out that way, that they shot more 3s than 2s. And in a moment, I'll show you a change on this problem where it would be more normal. So let's see what this problem is saying. That's saying that all of the shots that they took came up to 91 points. Okay, points, 91. It says that all of their 2- and 3-point baskets came to 34 shots on baskets. They took 34 that they put up. Okay. Now, how many of each were made? Well, in this case, and here's the whole problem, I wrote my definition of my terms. X is going to represent the number of 2-point shots. Y is going to represent the number of 3-point shots taken. Okay, that doesn't mean made, it's taken. Now, in this case, the number of 2-pointers plus the number of 3-pointers equal 34 shots. What are my units? Shots plus shots equal shots. For my second equation, 2 points each times how many shots, plus 3 points each times how many shots, equal to 91 points. Well, 2 times how many shots is points. 3 times how many shots is points. So points, points, points. Shots, shots, shots. I'm trying to show you a pattern here. Okay. Well, I got to find an opposite pair. In this case, I chose it to be the Y's. It could have been the X's just as easily. Okay. In this case, I multiplied everything in this equation by -3, resulting in this modified equation. The other one I just brought down. Okay, I combine them. And I get negative x equals negative 11, x equals 11, 2-point shots. Now I've got to finish. So I take this simple equation. Besides, they're asking what were shots, and this is the shots equation. And I put the 11 in here, and I get 23 3-point shots. Let's check this thing. 2 times 11 is 22. 3 times 23 is 69. And you add those, and it comes up to 91 points. Now let's look at a modification on this problem that wouldn't come up with such a goofy answer. Well, there, I put the numbers in. Okay, if I put the numbers this way, I'm going to get 2-point shots and 3-point shots. You work this one. Hint, it's worked just like the last one. First thing I did is I put down my legend defining my variables. Oh, come on, these numbers aren't so hard to need a calculator. Okay, those should have been your equations. Okay, I'm going to multiply everything by -3 in the top equation, which gives me an opposite pair of y's. You could have multiplied everything by -2, and you would have gotten an opposite pair of x's.
Why'd you put the by negative?
Say again?
Why'd you put the by -3?
Just to let you know what I did from here to here. I multiplied all 3 of these values by -3, so I could get an opposite pair.
Where would you get the -3 at to make sure?
Where? Well, I had to have an opposite pair, a pair of either y values or x values that would cancel each other out.
Oh, okay. So in this case, we'll just be canceling out the.
I'm going to be canceling out the y's.
Okay. So you could do.
If I multiplied by -2, here, here, and here,
It would cancel out
it
that.
would cancel out the x's. And you'd have a y value left. Okay, and you can do either. It doesn't matter. Well, I get -x equals -1, so positive x equals 21 shots on basket. So I take that 21 and I substitute it in the equation, and I get 8 3-point shots. And this will check. 21 times 2 is 42. 8 times 3 is 24, 42, 24, add up to 66. Now, this one's a little different. This one's going to be a little different. This one is a principal interest rate problem. I equal PRT. That's the fundamental simple interest formula. And it tells us in the problem we're going to use simple interest. As you recall from before, we had 3 interest formulas. We had the periodic interest that was recalculated, we had simple, and then we had infinite or continuous. And this one's just the simple interest one. So I equal PRT. Now, P ultimately will be $10,000, except we got a variance because they throw it in. They tell us that wasn't one lump sum that was borrowed. That part of it was borrowed from a Perkins school loan, and part of it was borrowed from his aunt. Okay. Now, it gives us some specific information of those. The amount that he borrowed from Perkins, they charged him 5% interest. His aunt gave him a sweetheart deal at 1.4% interest. Sadly, due to inflation recently, you guys would be probably lucky if you could get 6% or even 8% money. You know, I mean, that's just the reality. You buy a used car, you're going to be paying 7 or 8% probably. Okay. Now, this 428 represents how much interest on the Perkins loans amount plus the aunt's amount. Okay. Now, let's go through and see what we've got here. I'm going to let X be the amount of money he borrows from Perkins. Y is going to be the amount of money borrowed from the aunt. So, if this is the basic interest formula, it does tell us per year. That means 1 year. So that time is kind of a non-factor. Here's our first equation. The amount of money he borrows from Perkins plus the amount of money he borrows from aunt is 10 grand. So far, that's just like the other problems, isn't it? Well, let's look at our second equation. Don't you think we're going to take these two amounts and qualify them with the interest rate on each one? So in that sense, it's just like all of the other problems we've set up. Okay. And in this case, the amount of interest, or the interest rate times the principal, and the interest rate times the principal equals the total interest paid. So here we got amount borrowed, amount borrowed, amount borrowed, amount of interest, amount of interest, amount of interest. So I'm bringing these forward now. On this one, instead of doing an elimination addition method, which I could, it'd be nasty, but I could. I'm going to use the other method that was in my video, called the substitution method. Okay. In the substitution method, what you do is you isolate a single variable in one of the two equations. In this case, I choose to isolate that x by moving the y to the other side. Now, this 10,000 minus y becomes the substitution value in that equation. It's kind of like what we did in compose, where we substituted one equation into another equation. Actually, it's exactly the same thing, except we got two variables. So I'm going to this 10,000 minus y, and I'm going to put it where that x used to be. Everyone follow me before I go any farther. Well, I got to simplify this thing, so I got to distribute this. 0.05 times 10,000 is 500. 0.05 times y is 0.05y. And then I brought this down, I brought that down. I need to combine like terms. I can combine this and that together. Remember, line up the tables, round them out so they're all the same length. I got to put an extra 0 behind that 5 before I can subtract them and get this answer. Line them up, round them out, bring them down. Line up the decimals. Okay. Well, 2 come from, or negative 72. Minus 500, minus 500. So I've got y variables on one side, numbers on the other side. Now I'm going to divide both sides by that thing. That's now time to grab your calculator, find it on this problem. Up to this point, your calculator is really kind of useless. But at this point, it becomes useful. Well, look at this. 36 is half of 72. You actually could do that one, whoa, in your head. Everyone. So what does this 2,000 represent? This 2,000 represents the dollars that he borrowed from his aunt. Okay. Now, once we got that 2,000, it's easy to take this equation or that one and substitute in the $2,000 and figure out that he gave 8,000 or got 8,000 from Perkins. Okay. And that's your two answers that you need to have. And you would need a $sign on that unless you use the label that I had back at the beginning. Questions on this problem? Okay. Here we have a solution problem. You know what? This one's going to be set up almost the same way. We're going to have ounces of one solution plus ounces of the other solution equals total ounces. Then we're going to have percent times ounces, and percent times ounces equals total percent times ounces. So this one's going to be set up exactly the same pattern these others have. Okay, here's my legend. X represents the amount of 20% solution. Y represents the amount of 35% solution. Okay. In other words, we're going to have to raise this 20 up to 30. So we're probably going to have more of this one than we will that one. Okay. Well, let's see. Here's my first equation. The amount of ounces of the 20 and the amount of ounces of the 35 is 15 ounces. Ounces. Next, I'm going to have the 20% times the number of ounces, the 35 times the number of ounces, and the 15 ounces times the number, times the percent. I suppose I should have put these backwards from the way the order they're in to be consistent. Now, from this point, I could either use the substitution method or I could use the addition method. It's really up to me. In this particular case, what I'm going to do is I'm going to multiply everything in this, to answer your question, by -20. You're thinking -20. Well, we're going to actually multiply both of these by something. So I'm going to multiply this one by -20, and I get that, and I get this, and 15 times -20 is -300. This one, not only am I going to multiply out those two numbers, which is going to give me, in this case, 45, but I'm also going to multiply all three of these by 100 to move that decimal over two places everywhere. Whoops, went too fast. So I multiplied this one by 100, moved it over 2, moved it over 2, moved this over 2, and 15 times 30 is 450. I've got an opposite pair here, so those two go away. This gives me 15y equals 150, y equals 10 ounces. Well, if the 35% solution was 10 ounces, then that means the 20% solution had to be 5 ounces. 10 ounces plus 5 ounces equals 15 ounces. That's my check. Okay. Now, once again, I hope you're recognizing the pattern that you use when you set these up. Okay. That's probably what I'm trying to teach you more than anything on this. More than at this point than how to do the mechanics of it. This one now, earlier on, we did some directional problems. When you're going with the wind, your rate suffers, or your rate benefits, it speeds up. When you're going against the wind, then your rate slows down. So it was my old statement, what giveth, the river taketh. And you're probably, well, no, you're not the rower. We had that discussion before. Sorry. Anyway, we're going to have a plus and minus airspeed in this particular problem. Now, what does it tell us? This is basically a D equals RT problem. Distance equals rate times time. Here, on the flight against the wind, the time is 5 hours. With the wind, it's only 4 hours. In this case, they're going the same distance both directions. Okay. What else does it say? Well, it tells us what the distance is. Now, find the plane in still air and then the speed of the plane. Here's the speed of the plane. Here is the speed of the wind. Okay. And we're going to make a chart. There's our basic D equals RT. We're going to fill in the values for going and coming. So when you're with the wind, that means the speed of the wind adds to the speed of the plane. Now our distance is going to be 3,200 both times. But when you're with the wind, the speed or the rate is going to be the plane plus the wind. And the time against the wind, or when you're against the wind, then it's the wind minus the wind. Easy for me to say. And we got respectively 4 and 5 hours on these. Well, this gives us two formulas, two equations. It gives us those two equations. What is this? D equals RT. D equals RT in both cases. Except this one is the giveth and that's the taketh. So we simplify those by distributing, and they become that. And we can, at this point, either solve by substitution or by addition. And in this particular case, substitution wouldn't be very practical because we don't have any nice numbers in. Now, how do I know what to multiply these to get an opposite pair? It's basically a common denominator function. Okay? What's the common denominator of 4 and 5? No, not least common factor, least common denominator, the number that both of them will divide into. 20. Smallest number that 4 and 5 will both go into is 20. So I need to make these into 20 and that into 20. So I'm going to multiply this by 5. I've already got opposite signs here. And I'm going to multiply this whole row by 4. Except they're not multiplying, they are dividing. Here's a new trick. We could do this by 4 and have the 20s and the opposite pair and subtract. But look what they did here. In this case, they divided by 4 and divided by 5. 4 times 8, 5. The 5 goes into the 200 part of that. So they did that, and this is what these two equations became. You look puzzled or bored. I'm not sure which. Mm-hmm.
Oh, we're gonna.
Okay.
I'm sorry.
All right. So anyway, I do that. I do have an opposite pair, and I get this divide by 2, and that means that this plane is flying 720 kilometers per hour. Now, if you want to know how many miles per hour that is, take 0.6 times 720. Any of you ever looked on your speedometer where you got kilometers and miles per hour? At 100 kilometers per hour, that thing is 6 miles an hour. That's where that 0.6 came from, I just said. Actually, it's closer to 0.61. Well, anyhow, now we're going to take that 720 and we're going to substitute it into one of these two equations. And when we do that, we're going to get the wind speed was 80 kilometers per hour, which means in reality somewhere around 48, 49 miles per hour. So the plane speed, 720 kilometers per hour, the wind speed, 80 kilometers per hour. Still see some people writing. All right, here we go. Here's another one. Boat takes 3 hours to go 24 miles upstream against the current. Downstream, it can go twice as far in the same amount of time. Wow, that's quite a difference. What is the boat in still water and the speed of the current? Well, this again is a D equals RT problem. We'll let R stand for the speed of the boat in still, C for the current. And we're going to have a plus and a minus current. So here are my two equations. It goes when it's going against the current. current's fighting it. They go 24 miles in 3 hours. When it's with the current's pushing it faster, 48 miles in 3 hours. Now we simplify that. I guess I'm going to have to do that. So in this case, 24 equals 3R minus 3C. 48 equals R plus 3C. I've got a natural opposite pair here. So in this case, 24 plus 48 is 72, I believe, equals 6R. Divide by 6, and we get R equals 12 miles per hour. And what is that 12 miles per hour represent? The speed in still water. That's the speed in still water that this boat's going. Now let's find out what C is. So we take that 12 and put it into either one of these, probably one of these two equations. 24 equals 3 times 12 minus 3R. 24 equals 36 minus 3R. Take this 36 over to the other side, and I get negative 12 equals negative 3R. Everyone with me on that? Divide by 3 on our negative 3 on both sides. And I get R equals, in this case, 4 miles per hour. And that is the current. Okay. Well, you see these two D equal RT problems are fundamentally the same. Yes.
If this is current, why is it an R? I thought current was C.
All right, excuse me. Thank you for catching that. How about if I replace all of these with C's? Now better? Thank you. Yes, that was carelessness on my part. Because obviously that's a C there. Okay, any questions on before I start erasing this one? All right. Now, here's where we've been. Okay. Now we're going to deal with 3 equations, 3 unknowns. Now we're talking 3-dimensional space. Not only have we got up and across, but we've got in and out. Okay. So now we're dealing with 3-dimensional space in this. And it takes a little bit of visualization sometimes. Now, here are some possibilities. I need to show you something before you realize that. Any 3 points in space, here's 3 points, my fingertips. Okay? Any 3 points can make a flat plane. They will define that plane, and they make that plane rigid in space based on where they are. Okay? And that plane continues in all directions in that same direction. Okay? That's what these are trying to represent. Now, have you ever seen a four-legged stool that wobbles? A four-legged, I bet you have. Kind of like the table I had in a restaurant the other night, just irritated the heck out of me. Every time I got ready to dig into my plate, this table bounced. A three-legged table won't wobble, neither will a photographer's tripod. And that's why they use a tripod, not a quadrupod. Okay? So, at any rate, there are some different possibilities. There are 5 different possibilities if you had 3 distinct planes. Now, we're going to write equations that have x's, y's, and z's in them. So these equations, when you have just simply an x, that's a point on a line. If you have an x and a y, then you've got graph paper. And when you have an x, y, and z value, the equation will give you the direction of a plane. Now, with these 3 equations, I could have purple plane, I could have this green plane, and I could have this flat yellow plane. It's possible they could all intersect in one point. Okay, and that's the case, obviously, be consistent, and those planes are independent. But you know what? Those 2 classifications aren't important in this. I'm just relating it to the previous. The 3 planes could be used to build an A-frame house. Here's the peak of the roof, where the 2 planes here meet. And this peak is in the form of a line. Likewise, where the walls meet the floor. 3 planes, each intersects each other in a different place, but there is no one common point of intersection. That means somewhere we're going to get an answer like 0 equals 3. Okay. Parallel, we've talked about parallel before, right? No common solution again, are there? This one, all 3 enter in one line. And that's possible. They can create one line. And then finally, kind of like lines when we have the stacked lines, where you got the solution 0 equals 0, 5 equals 5. Well, that's what these are, is that's all 3 sheets of paper are actually the same equation, just in different form. So those are the different possibilities. Now, you've got this page in your packet. I believe it's page 16, if I'm not mistaken. If you'd get that out. Looks like this. Now, they're going to have a set of rules or a set of steps in a few minutes that are slightly different than what I've got from here. I'm going to show you what the difference is, and it's very minor. Where I've got equation 1, 2, and 3 that you start with, they call them A, B, and C. When I say here, you're going to create equation 4 and create equation 5, they call them equation D and E. That's the only difference between my set of instructions and the way my slides are going to show it. Okay? So, what are we going to do here? Well, you can read through that. You've got it right in front of you. Here are 3 equations in 3 variables. This is the equation of some flat sheet of paper. That's the equation of a different one and a different one yet. Okay? Now, in this one, we will use repeated addition elimination methods, finding opposite pairs. Okay? Now, the general plan on a problem like this is you pick equations and you eliminate one variable from those two equations, getting an opposite pair. In this case, okay, it says choose two and eliminate one variable. There's equation A, B, and C. And I'm going to choose to eliminate Z because overall it's kind of got the nicest numbers when you compare all three equations. Okay, so I'm going to use equation A and equation B. Now, equation A I brought down just like it was, but equation B, so I would have an opposite pair. I multiplied all of equation B by a -1, making this -2x plus y plus z and +7. I add the two equations. The z's go away. I've got the x, the sum of the y's, the sum of the numbers. Now I'm going to label this equation D. And it's really kind of important that you do label these equations, okay? Now, the next thing we're going to do is we're going to repeat this process, except we're going to use two different equations. We can't use A and B again. We can do A and C, or we can do B and C. But we just can't use A and B again. So I'm going to choose, in this case, I'm going to choose A and C. Now, with the C equation, I brought down just like it was. The A equation this time, I multiplied everything by 2, 2x, 2y, -2z, -8. So I would have an opposite pair of z's again. I've got to eliminate the same variable.
Where's that red mark under the two? What's the? That is C.
That,
Down below. Under the two.
That?
Yeah, what's that?
an E,
So that's good.
that's a script E.
Oh.
Because when I add these two together, my answer is going to be a new equation.
Okay.
Like that. Here I have these opposite z's, so they go away. So I have the sum of the x's, the sum of the y's, the sum of the numbers, just like I did up here. And so I get this equation in x's and y's. I'm calling equation E. This equation in x's and y's, I called equation D. Now, everything we've been doing before we started this, we had two equations, two variables, and we solved those. So that's what we're going to do with these two equations, these two XY equations. So if everyone is ready, I'm going to my next slide. I'm going to take this D equation and this E equation is what I'm going to do right now. There's my D and there's my E. We can solve these just like we've been doing all night. I don't have a opposite pair right now. Probably, in my opinion, the easiest way to get one would be to multiply this one by 3. And in fact, that's what I'm going to do. When I multiply that by 3, here's my modified D equation. The E equation I just brought down. I do have opposite pair, so I combine those and those respectively, and I get y equals. Now, what we have done Okay. In this particular case, we have found that on our 3-value term, the y value is 0. What we're trying to do is we're trying to see if these all intersect at one point, just like we were doing with the 2's earlier. So now let's take that 0 and put it into either one of these equations and get the x value. Particular case, I chose equation D. I replaced y with 0. Negative x equals 3, x equals -3. So I now have 2 values of my point. Now, with 2 values of the point, I can go back to equation A, B, C, any of those 3 equations, substitute in these 2 values, x equals -3, y equals 0, and find out what z is. In my case, I chose the equation A because it was the simplest one. So I put the -3 in for x, the 0 for y, and I got z equals ultimately +1 with a little bit of arithmetic. Now, having gotten that value, here are my 3 values. So here is my common point of intersection. You remember those displays of angles that I had at the very first slide? This was the very first one because they have a common point of intersection. Okay, here's another problem. We got a little bit of arithmetic to do on this one to clean it up a little bit. First thing I'd probably do is multiply all 4 of these terms by 6 to get rid of those 2 fractions. So if I multiply this equation by 6, I get that equation. This one, I'm just bringing over. That one, I put the 3y. You have to have these in the same order. That's kind of important. I haven't mentioned that previous. Although I think I did mention it on the XY problems before, yes.
So did you choose 6 because?
It's the common denominator of 2 and 3.
Okay. And the same, but that's the only one that you would choose. You don't. get the
And
others.
all I'm doing is getting rid of the fractions on that one. I haven't started figuring out what I want to eliminate yet. Although looking at these, z's are going to be the easiest to eliminate first. Okay, so I'm going to find an opposite pair. I'm going to use A and B again. Now, because this is a 2 and that's a -1, I'm going to have to multiply this equation by 2, so I'll have a 2 both places. So I took 2 times all of the B equation, giving me that. Now I've got an opposite pair of z's. So these 2 are going to cancel out. And then that's going to leave me remaining 8x minus 5y equal 28. And that's my equation D. Do the same thing, except with A and B, I'm either going to use A and C or B and C. So I involve all three equations. So I'm going to do B and C. In this case, because they both already have an opposite, I don't need to multiply either one of them by anything. Because those z's will cancel just like they are. So that gives me the xy equation of this. Here I have the xy equation of that. So I've got two xy equations, so I can work them together to solve my first variable. So here's those two xy equations. Did I change too fast for anyone? Okay. Common denominator of those two, if I wanted to make it the one that I eliminate, would be 56. 2 is 10. Which one I'm going to use? The 10, right? So I'm going to multiply that by 2 and that by 5. Giving me those two equations. My negative 10y and positive 10y will cancel each other out. And ultimately I get x equals 1. I'm going to take that x equals 1 and I'm going to put it into either one of these two equations. There's the 1. And I get y equals 4. So I now have two of the three values. I go back to equation A. I could use B or C. Substitute in. Here's the 1. Here's the 4. And I get z equals 6. So therefore, my solution is the point 1 negative 4, 6. We're going to skip that one over and go to this one. There's something special about this one. It's got some missing parts. Now, the first thing we're going to want to do, we want to fill in the missing parts. Okay, if y is not shown, then it's 0y. So here's equation B. Equation C, I can eliminate the z's right there without doing anything else. Excuse me, I breathed something I should have swallowed earlier. It's still bothering me. Okay, so I get 3x plus y equal 33 for equation D. Now, because in equation A, I only had x's and y's, I don't need to figure out an equation E. Because I've already got two equations that are just x's and y's. So I put those two together. I've got to multiply one of these by a negative. Whoops. Multiply it by a negative. Got an opposite pair, and I find out x is 7. I substitute that 7 into this equation, and I get y is 12. Now I take this 7 and 12, and I put it into one of the original ones, equation B, that is z. In this case, I don't need to use 12. I just put in the value for the x, and I get z equals 10. So my solution then is 7, 12, 10. Question? All right. We're going to change directions again. Now we're going to deal with linear inequalities. We're going to be dealing with lines initially. This is standard form, except you're used to seeing an equal sign here. Okay. We've done a little bit of this with lines before, a single line, but we're building to multiple lines. Except we're going to replace an inequality where the equal sign used to be. The process of graphing these is just like it would be if we had the equal sign there. Now, here's an example. I'm given this equation. This is a line. Now, they're going to do it the hard way and find the intercepts and graph them, draw the line, but you don't have to do it the hard way. Here's the line. Y-intercept is -4. Slope is 1. Up 1 over 1, up 1, up 1, up 1 over 1. And so on. Okay? So I graphed that. Now, because there is no equal here, I have to use a dashed line to indicate the non-inclusive. We've got the greater than symbol. Now, what that greater than symbol means is the actual included value of y's is anything that's bigger than a y value that's on the line. That's the way you need to think of this. The y values of the answer is anything bigger than whatever the y values are on the line. So if I've got this point here where y is -4, -2 would be bigger, 0 would be bigger, 5 would be bigger. Likewise, down here, if y is -1, then 0 would be bigger and so on. And that's why I'm showing these arrows in this shaded region. And the shaded region would be your answer on this graph. Questions about this one? If you got it in standard form, they're going to try to have you pick points and just try them by guess and by golly. But if you put it in y = mx + b form, then you can read off whether it's above or if that's a less than below the line. Okay, now here's just some general instructions. I don't know that you need to write that down. I'll let you read it for a moment. Okay, here's another example. This time they gave us the equation in standard form, only with an inequality. Here's what I was talking about, them using the intercepting, where you let x be 0, you let y be 0. And is that point in the shaded area or is it not in the shaded area? Well, you know what? We're not going to do it that way. We're going to convert this. And by the way, there needs to be a 2. This is supposed to be a 2 right there. We're going to convert that into y = mx + b. So what we're saying now is this time the region count is all the points below or on the line defined by this. So our y-intercept is 4. Slope is -2. 1, 2 over 1, down 2 over 1, down 2 over 1. This time with a solid line because it is an or equal. Okay. Now, let's analyze then the region. Points smaller than, y value smaller than the ones on the line. So it would be all of these. And of course, this thing goes forever and keeps going out this way too. That's what we've got on the questions on this one. Here we have a vertical line. We've got the line x equals 2, except it's dashed because that's doesn't include the equal sign. Now, this is really pretty easy. We don't need to do this truth or false steps. Just simply look at this. Where are x values bigger than the on the line x equals 2? Well, 3, 4, 5 is bigger than 2. So everything. Here's a horizontal line. In this case, the standard form y equals 2 would be defining this line. This time I do have an or equal, so I use a solid line. Now, what part of the graph is below the line y equal 2? Well, it's all of this. So those are really pretty simple. If you break this down, put it in ymx plus b form, or in the case of horizontal and vertical lines, it's really very easy to determine what's your shaded region that you would have of possible answers. Believe it or not, any point down here in this green would make that thing true. Now, here's another one. Now we're going to go to 2 equations. Now, instead of having to solve these by addition or substitution, we just solve them by graphing. In this case, we're going to graph this one, so we've got to put it in y equal mx plus b form. Likewise, this one. Here's the conversion on those. I have an equal, so I'm going to have a solid line on this one. I'm going to have a dashed line on that one. I did have to flip the symbol here because when after I took the x over, I had to divide both sides by -1. And when you divide or multiply by a negative on both sides, you have to flip symbol. Okay, so you got to watch out for that little detail. We're not going to deal with the test points because we're going to use the analysis of above and below. So here's the graph. On the first equation, the y-intercept is 3. The slope is -1, down 1 over 1, down 1 over 1, down 1 over 1. The line is solid. Now, shaded area, all areas bigger where y is bigger than the ones that are on the line. So my green shading. The second equation, y-intercept is -1. The slope is +1, up 1 over 1, up 1 over 1. It is a dashed line because of the inequality. Now, the area, values below the line, y value smaller than the ones on the line. So that's everything down this way. Now, if you look at the shaded region right here, where this overlaps, that's the solution on this. Okay, that is the solution on this. And that's the way you're gonna show your graphs when you do these. Question on this one before I go to the next one. Okay. Well, here's just the sum up of what I said there. Okay, now. This was 3, we're not, well, I'll show it to you.